All right, good morning, everyone. We're going to focus our attention today on working through the first page of the chapter 4 review worksheet 1, and we're really going to take advantage of the calculator features that we talked about yesterday, and we're going to see how they're going to help us through this process. Okay, so today we're going to focus mainly on calculator work, and so I'll go through slowly, show you all the keystrokes, whether you're using the 84 or whether you're using the 36 Pro. Get comfortable with the types of questions that we may be expecting on the test that is calculator focused, and then tomorrow we'll go back and talk about work through the problems that involve you to show steps like use substitution, finding definite integral, power rule. So, and then on Monday, I will put it all together, do a final review. I'll share with you exactly what type of questions to expect on the test, and then test on Tuesday. Okay. So let's read number 1 here. It says particle moves along the y-axis. So this is a particle motion problem, but I think we're more used to seeing a particle moving along the x-axis, right? Horizontal. Back and forth. Left would be negative velocity, right would be positive velocity. But in this case, we just have to make that adjustment. Now, this object is restricted to a vertical motion along the y-axis. So it's either motionless, going up, or it's going down. So we're going to have to make some slight adjustment. That means positive velocity is not going to be associated with upward motion, and negative velocity is now going to be associated with a downward motion. So we have a velocity function given to us, t sine of t squared. Let me write this a little bit larger here. So that means if I put in any t value, in return, it'll give me a number, and that number is going to tell me the velocity of that particle. Okay. So part A, it says, in which direction is the particle moving at time t equals 1.5? So how do we go about with this problem?
1.5, and if it is positive, then it's moving up, negative down.
Good. So we have everything that we need in front of us, right? There's no need to find the integral, find the position. There's no need to find the derivative yet with acceleration. We can rely directly on the function. So we can enter this in the calculator. Now notice that we're dealing with a trig function here, right? So it's important that you are in radian mode. I would say just always have it in radian mode, but this is where radian mode is going to make an impact. Okay, if it happens to be in degree mode and if it's not trig based, then you'll be fine. But you're going to get answers that are way off if you are not in radian mode and you're putting in trig functions. So just make sure, double check, go to mode, make sure in radian mode. Okay. Okay, so I'm going to just, if I want to find velocity at 1.5, just going to put 1.5 in for wherever I see my t values, and just going to enter that in. Okay, 1.167. And let me talk about approximation here. You're going to round to 3 decimal places, and that is what they want on the AP exam as well. But sometimes, so you have 2 options here, either round to 3 decimal places and just cut off that, just don't look at any number beyond it. Or sometimes you can also do this. If this number is rounding this to a higher number, let's say it's 1.1678, you can round this up to 1.68. So either you take that third number, make the fourth number rounded, or you can cut it off. Either way is acceptable. Okay, just want to give you options there when you're rounding to 3 decimal places. Okay, so V of 1.5, 1.167. So which direction is it moving then? Up, positive, greater than 0. We know that this particle, that's our justification, right? Particle is moving up. At t equals 1.5. Because velocity is greater than 0. Okay, any questions with part A? Now I want to go back to the calculator because I want to kind of show these shortcut methods that we can do, because we're going to be continually calling the same function, whether it's derivative or integral or something else. And rather than having to type in the keystrokes for that expression every time, if we have it stored somewhere, then we can just have it called and we'll just save some time with keystrokes. So it's not required that you do this, but I want to show it to you. Some of you may want to take advantage of shortened keystrokes, and I'm going to show you on the 84 and the 36 Pro. So let's go back to our function here. Here I did not enter in the function. I just plugged in directly for t, so I did everything manually here. But I'm going to try this from a different perspective. I'm going to have this function stored somewhere. I'm going to store it under y1. So it's the first button on the left there. If you click on y1, normally this is what we would do if we were to graph it, but we'll explore the graphing maybe a little bit later. So I'm going to type in my function, but remember, when you're dealing with your calculator, you're always using the variable x. Okay, don't try to match with other variables; it'll complain. Okay, so always use x. So instead of t sine t squared, I'm going to put x sine x squared. So x sine x squared. Okay. From here, I'm going to go back to my home screen. So to go back to the home screen, go to second mode. That's going to exit out of this window here. And now I'm going to take that 1.5. I'm going to plug it into my velocity function. So I'm going to call that function. So here are the calculator steps. You're going to go to vars, yvars function. That's going to help get you to that y1, which is storing our velocity function at this time. So there's a vars button next to the directional, 4 directional arrows here. So do vars, okay, then go to yvars. So scroll over, hit enter, function y1. So there is where my y1 is stored. And now if you do parentheses 1.5, what's going to happen is it's going to take that 1.5, it's going to insert 1.5 into all the x's of your function, and you can quickly evaluate without having to enter everything manually one at a time. Okay, so any questions with the graphing part? Okay, let me show you on 36 Pro that we can also have it stored somewhere. And it's going to be stored under this table. Okay, so go to table. We're going to edit function. And if you have something there, you can clear it. I'm going to enter in the same thing that I entered here, x sine x squared. And then your x button is next to the 4. Now make sure that in order for this to be saved, you're going to have to hit enter multiple times until you get to a table of values. Then you know that it's stored, and you know that you can call it. Okay, just keep hitting enter until you see a table of values. Now, we know it's stored under this f of x, so go back to your home screen, second mode. And now hit table again. And now we're going to call the function. Edit function allows us to change it. Now we're going to choose 1 because we're going to call it. So now, just like over here, instead of y of 1.5, I'll do f of 1.5. So what's going to happen is it's going to go to that stored function. It's going to replace all the x's with 1.5, and it's going to give back the value. Okay, so save a couple of keystrokes, especially if we have to keep calling the same functions over and over again. Okay, any questions? You guys okay? Okay. All right, let's go to part B. Find the acceleration of the particle at time t equals 1.5. So we have velocity. What's that relationship going to be? How can we get to acceleration? Derivative. Okay, so let's think about, if we want to do this by hand, you have to go through product rule. F prime g plus f g prime. There's a little bit of chain rule here as well. But it's a calculator question, so let's take advantage of our calculator. We're going to make the calculator find the derivative for us and plug in that 1.5. Okay, we're going to make it do all that within just one step. So let's go to our calculator. Math 8 is where our derivative feature is located. So you're going to do d over dx. Now you're more than welcome to type in x sine x squared in this location. But because I have y1, because I have my expression stored under y1, I'm going to keep calling that y1. So again, the way you get to it, go to vars, scroll over to yvars, function y1. So I have my function stored in here. I'm going to ask it to evaluate the derivative at 1.5. So what's going to happen is it's going to take that 1.5, dump it into the derivative of my velocity function, which is my acceleration. So I can say v prime of 1.5 is equal to a of 1.5. Now, you don't have to do both. I just want to show you that, you know, there's a couple of ways to represent acceleration, either v prime or a, and we get negative 2.04. So you have two options here, either leave it as 8 or push that up to 9. Either way, 3 decimal places. Any questions with keystrokes on the 84? Okay. Same. There's a derivative button there, second natural log. d over dx. Oops, dx is already there. I'm going to call the function. So something a little bit different here. You're still going to go to table. You're still going to go to f. But we're not going to stick that 1.5 in here. You're going to make it a function. So make go to next to 4x, and when you make it a function, make sure you close the parentheses because we need to have a matching pair with our parentheses. So close the parentheses. So you have f, 2 parentheses, sets of parentheses for the x and then for the f of x. And now you can put that 1.5 in here. Okay, any questions with keystrokes? All right, so let's go back to our problem here. Our acceleration is negative 2.049, but it's asking something else here. It's asking, is the velocity of the particle increasing at t equals 1.5? How do we interpret this?
Well, opposite signs.
Okay, let's see. Now, if the wording was, is the speed of the particle increasing, decreasing, right? So yesterday, if speed is increasing, decreasing, we compare signs, right? Same signs would be increasing speed, opposite signs would be decreasing speed, but there's a slight adjustment here. It says velocity, but it says is the velocity of the particle increasing. So what is this referring to? Just acceleration. I know we see the word velocity, so why isn't it dealing with velocity? Yeah, so that, right, it's a very subtle word there, right? That increase changes everything, right? It's not asking is the velocity positive or negative. It's asking about something that's increasing. So this is changing it to the rate of change of velocity, which is acceleration. So it's a roundabout way of saying, is acceleration positive or negative? And here, my acceleration is negative, so therefore, velocity of the particle must be decreasing. Okay, put a star next to this because you can expect something like this to show up on the test. So what if I had changed this problem here? What if I had said, is the speed of the particle increasing at t equals 1.5? How would you answer that?
And that's different sense.
Yep. So now we can look at both our results that we pulled up. Velocity is positive, acceleration is negative, opposite signs, speed is decreasing. Okay, so those are the reasonings, right? So any questions with that? Good. All right, part C. Given that y of t is the position of the particle at time t equals 0, sorry, at time t, and that y of 0 equals 3, find y of 2. So let me point us to the formula sheet. I keep updating this formula sheet as I find more things to put on it. So we talked about yesterday how we have a formula that allows us to find a position of a particle, right? So the idea is that if I'm looking for a position of a particle, I'm going to have to know, have a starting point as an anchor, and then the displacement is how much progress in terms of motion did this particle make between the two time intervals. So if I have a starting point plus how much progress I made, then if I add those together, that's going to give me the location at that particular time. But this is in terms of x, so we'll make a slight adjustment. We'll do this in terms of y to indicate that it's moving along the y-axis. But I'm just going to copy this formula here and adapt this for y. So I can say final position is equal to the initial or starting position plus the motion, the amount that we're going to, the amount of progress that we're going to make between that time interval, add those together, that will give me my final position. But in this case, I'm looking for y of 2, so my a is 0 and my b is 2. So y of 0 is 3, so that means I'm starting on the y-axis at the value of 3, and then I'm going to add or subtract depending on how much progress I made in that time interval. But we're going to go to our calculator to help us find the amount of progress, the displacement that this particle achieves. So Math 9 will get you to your integral notation. 0 to 2. My velocity function is x sine x squared, but again, we keep calling the same function, so I have it stored under vars. .827. So this tells me that between 0 and 2 seconds, this particle is going to move up 0.827. So if I know that I'm going to make that progress in that time interval, I'm going to take that progress, add it to my starting point, and then I'm going to know exactly where this particle is going to be located at t equals 2. So it started at 3, it made a progress of 0.287, so it's going to end up at 3.827. Okay, 36 Pro. Def to integral, second E, from 0 to 2. I have it stored under f of x, so go to table, f, make sure you fill that with an x. X is next to the 4. Close the parentheses. .827. All right, any questions with C here? All right, part D, find the total distance traveled. We have a formula for that. Total distance from yesterday's notes. Total distance is the integral of the absolute value of v of t. So very similar to displacement. We're just now putting absolute value around velocity. So integral from 0 to 2. I'm going to ask for proper notation on the test, so I want to see proper notation before you give me the answer. Now there's a keystroke for this on the calculator for us to get to that absolute value. So on your summary sheet here, let me go through those keystrokes here. Absolute value is stored under math number ABS. So this is going to be the same keystroke between the 84 and the 36 Pro, so that's good. But I'll show them on both. Absolute value feature, math number ABS. So math 9, pull up your integral notation. We're going to go from 0 to 2. I want the absolute value bars to show up. So math number ABS. Absolute value bar is going to show up here. I'm going to insert the function in here. Again, I have it stored under vars. So vars, y vars, function y1. Okay, questions? Just be aware that absolute value takes a little bit longer for the calculator to process. So it's not too bad here, but I think it takes a little bit longer on the 36 Pro. So total distance is 1.173. Second integral, 0 to 2. Same keystrokes here. I'm going to find math number ABS. I'm going to call that function. So table f of x, close my parentheses. Yeah, it takes a little bit longer here, but eventually it's going to show up as 1.173. Okay, any questions? Before we move forward, let me just point something out as an application here. My displacement is 0.827. My distance is 1.173. Same interval, different values. What does this tell us about this particle?
It must turn around at some point.
It must have turned around at some point, right? So the reason why this displacement is not as high as distance is that it's not going as far as it could have gone, because in that time interval is backtracking. But the distance is keeping track of all that back and forth, right? So if you see that your displacement is lower than your distance, you know that there's some backwards motion along the way. But if the displacement is equal to the distance, then what does that tell us? Yeah, it would have just gone in the same direction the entire time and didn't move. Your displacement is never going to be larger than your distance, right? So this is the highest that the displacement can go. It's either the same or it's less than that. Okay, just want to revisit those the idea between displacement and distance. Okay, they showed up here, 1.173. All right, good. Any questions with number 1? All right, number 2. The temperature in degrees Celsius of the water in the pond is a differentiable function. So differentiable function, that just means it's a smooth curve. There's only 6 order pairs here, but we know that there's no strange behavior between. There's no like holes or asymptotes or sudden sharp turns. It's just going to be a smooth curve. We have a very limited picture of the graph, but we know ultimately it's a smooth curve. Okay, the table shows the water temperature as recorded every 3 days over a 15-day period. So that means on the 0th day, it's we're taking the temperature once and it's coming out as 20 degrees Celsius. 3 days later, take the temperature again, 31 degrees. 3 days later. Okay, so we just very limited data, but we're using this to do approximations for A and B. Okay, so use data from the table to find an approximation for W prime of 12. So we see that notation, W prime of 12, we're thinking derivative, right? But we don't have a function to find a derivative. So, and it says approximation of a derivative. So derivative is just another word for what? For slope. So that is our way in with approximations. So what information do I need if I want to find slope?
Ordered pair.
How many order pairs? 2. I need 2 order pairs. So which 2 order pairs do you think would be a good approximation? If I want to do W prime of 12.
Maybe 12.22.
Okay, 12, well, that's 1 order pair. Okay. What's the second order pair? So we have a couple of options, right? The idea is that if you choose order pairs that are relatively close to your target, then that's the best that we can do, right? I mean, ideally, we have something a little bit closer than 3 days apart, but that's as best we can do. So you can either choose these 2 order pairs, you can choose these 2 order pairs, or you can also make an argument for what 2 pairs. There we go. Yeah, so these 2, right? But we want to restrict ourselves to one of these options, right? If we choose things that are too far away, then we're giving more options for things to change, and then our approximation is not going to be as good. I mean, our approximation is not going to be great anyways. It's 3 days apart, but based off of the data, that's best we can do. So that means that there are some variations to our answer because we have some choices. I'm just going to choose these 2, but if you choose any of the order pairs around these, that will be correct as well. So W prime of 12. We know it's not perfect slope, so we'll put a squiggly to indicate it's an approximation. So change in temperature over change in time. Okay, what's the unit of measure here?
Degrees Celsius per day.
Degrees Celsius per day. All right, so what does this mean? What does this mean without using math terms like derivative or slope? What does this tell us about the pond?
The temperature is decreasing by a rate of like -1/3 Celsius a day.
On that 12th day. Good, right. So basically it's just a rate of change. It's telling us it's It's very minimal, but as best as we can observe, on that 12th day, our temperature is dropping very slightly by a rate of 1/3 degrees Celsius per day on that day. Good. All right, part B. Approximate the average temperature in degrees Celsius over the time interval from 0 to 15 using trapezoidal approximations. So let's focus on these words here first. Average temperature. So that's an indication that we're going to be using average value theorem. I'm going to add this to the formula sheet here. Average value theorem is basically area divided by the width equals the height. But in this case, our height is going to be our average temperature. So I'm going to put this over here. Average temperature is 1 over b minus a integral from a to b, in this case of w of t. My a and b values are 0 and 15. So we can say average temperature 1 over 15 minus 0. Okay, any questions so far? Now, look at this portion here. This is written as a calculus notation, but we don't have a w of t to plug in, right? We don't have a function that we can use. So the best that we can do, we know that this is some integral notation for area. The best that we can do is use geometric shapes because we have a table of values. So if we're doing approximation of an integral, that means we're resorting ourselves to either using left Riemann sum, middle rectangles, right rectangles, or in this case, trapezoids. So we're going to approximate this area using trapezoids. So the trapezoid is after the same goal as this, but it's just from an approximation standpoint. But the goal is still the same. We're still trying to get to that area under W of t graph. So let's think about trapezoids here. We know that there's a width component to it. What do you notice about the width of each of these subintervals? They're all the same, right? So if they're all the same, what we can do is normally, I would say, that we got to find all these trapezoids separately, right? 1/2 width, height 1 plus height 2. But because we have all the same width, we can kind of merge it together into a formula, and we can use trapezoid approximation. So trapezoid approximation is where we can factor out the width, and then we can just total up all the heights. But with trapezoids, we have all these shared heights in between, so all the heights are going to be doubled except the ones at the end. So I'm going to be adding up all the heights, but then I'm just going to double all the ones in between except the ones at the end. So those will only be used once. So average temperature, 1 over 15, that's a coefficient. And now I'm going to insert this formula in place of this, because I can't get an exact value. The best I can do is do some geometric approximation. Okay, so 1/2, my width is 3, and add up all the heights. But all the middle ones, I'm going to multiply by 2. Okay, that's just a matter of entering all that in the calculator. So I'll jump to the calculation here. Ends up giving us 1/15 of 376.5. And that's going to get us 25.1 degrees Celsius. Okay. If we just look at these values, is that 25 degrees going to make sense? 20, 31, 28, 24, 22, 21. Okay, so we can look at that, and that's reasonable, right? Reasonable average between all those heights, between all those temperatures. So the reason why I say that is because let's say you forgot about that 1/15th, and you're staring at that 376.5, and you're saying, okay, does that make sense? Is 376 degrees going to make sense with all these values I see in front of me? Okay, I must be missing some things. That's too high. Okay, we need to include that 1/15th here. We're dividing that area divided by the width, and that's going to give us to the height, which is our average temperature. Okay, so those A and B is kind of focused on the approximation side of things. And now part C and D, we're going to have a function that will actually give us more detail about the change in temperature in the pond over this time period. So part C, a student proposes a function P of T, which is a model for the temperature of the water in the pond at time T. So it's after the same information as here, but it's a lot more detailed. Instead of just 6 points, now it's going to be able to find temperature at any on any day and in between days over the course of these 15 days. Okay, so we have a model for the temperature of the water in the pond at time T, where T is measured in days, P of T is measured in degrees Celsius. Find P prime of 12. So we're kind of back to what we were doing for part A, but now we have a more accurate way of approximating, or now it's not an approximation. Now it's going to be potentially exact because we have a model here. So now that we have a function, we can use the calculator to find the derivative at 12, right? Find the rate of change of the temperature on that 12th day. So 84. I'm going to I'm going to call this multiple times here. So I'm going to go to Y1 and have it stored under my Y1. Use X wherever you see a variable. Once you're done, do second mode to exit back to your home screen. We're finding the derivative, right? So math 8, d over dx, bars, y bars function. So there's my temperature formula. I'm going to plug 12 into its derivative to find the rate of change of temperature. And if you look, it should be something similar to part A. It's just a more accurate version of part A. Okay. Units of measure, same thing. So A and C are after the same goal. It's just that one is an approximation and one is more accurate, or one is based off the model. So same idea here, right? Temperature is dropping. On that 12th day. Okay, same thing here. You can go to table, edit function, type in that function here. Oops. enter all the way till you see the table of values, so you know that it's stored. Okay. That second natural log will get you to your derivative feature. Put in the function, make sure you put an x and the close parentheses, and evaluate it at 12. Okay, questions? Okay, part D, use the function defined from part C and use it to find average value. So we're kind of back to where we were with part B, but now we're going to be able to rely on exact integral rather than approximation using geometric shapes. Right, so we're after the same goal, but just calculus methods here. So average temperature, same formula, 1 over b minus a, but I have a special name for that function, right? It's p of t now. So 1/15th. We can do, there's actually a divisional math print on some of the 84s if you have it. If you check it with, if you do second y, there's that n over d feature, which you can get that fractional notation to show up just like on the 36 Pro. I can do 1 over 15. I can avoid having to put in parentheses for order of operations. And then math 9, 0 to 15. I have my function already defined under y1. (25.757 degrees). And it should be comparable with part B. It's just a more accurate version of it. So they're both after the same information here. Okay, any questions here? Okay, no questions with the calculator? Okay, one last thing I want to talk about is I want to talk about what I added to this formula sheet. We talked about first theorem of calculus, where if I take the integral of a function with definite integrals, it's going to turn itself into the antiderivative, and then I plug in upper and lower bound. Right, we can do this for problems by hand. Right, if we do power rule, we can get that function. But I also want to show you that we have all these different variations of first theorem. As long as we have that relationship of a function turning into its antiderivative, we can do it for a lot of different variations. So I want to show you that just based off of this, we have a variation of, well, if I start with velocity, integral of velocity will push it up to position, and I can do position of the top bound minus position of the lower bound, right? So that's a variation of that. We can also think of it as, well, if I start at f prime, then f prime will move up to f of x, then I can plug in my upper and lower bound here. If I start at f double prime, I can also use this for first theorem. Second derivative will turn itself into f prime, plug in upper and lower bound. If I start acceleration, I can also apply first theorem, push acceleration into the velocity region, and then v of b minus v of a. So it looks daunting that there's all these variations, but it's just kind of just taking this relationship and then applying it for all these situations, right? So as long as you have something that, and sometimes it's nice to have these variations in case we need to create an equation and be able to plug information in. If we understand these variations, we can adapt it for any situation. Also, we use this a lot, right? Where final position equals initial position plus displacement. There's also a variation of this, which is saying, well, what if I start with velocity? So I can say final velocity equals initial velocity plus the accumulation of velocity over that period of time. Right, so I'm just taking this and just adapting it for different at different levels. Okay, any questions? So I'm going to be skipping this third page, this problem here. It's an important problem, but I may just go ahead and save this type of problem for when we get to AP review, just because the amount of material that I want to cover, I'm going to focus on other things first. So let's just be able to do problems like 1 and 2. So maybe we'll revisit these types of calculator questions again, maybe Monday. But tomorrow, I want to focus on these non-calculator type questions where we either have to do something with power rule or use substitution or change a variable or involving trig use substitution or involving evaluating definite integrals after we go through use substitution. So, and let's give you a preview here. Second theorem, where we know that derivative and integrals are going to cancel each other out. We just have to know what to do with those bounds. Probably not going to have any absolute value by hand. And yeah, so I think, and then the even odd functions, we'll review a little bit of that as well. Okay. All right, thanks everyone. I'm going to have a help session this afternoon, 3:30 to 4. I may have a help session tomorrow morning as well. If I do, I will send out a remind. Okay. All right, have a great day, everyone. See you tomorrow.